hope that you can hear me, and I hope the latency isn't too bad. All right, cool. So let me see, I'm gonna see what this latency looks like. Next slide. All right, looks like there's still quite a little bit of latency. I don't really know if there's anything I can do about that at this point, but yeah, I guess we'll get started here. So, hi everyone. My name is Jack Koenig. I am one of the maintainers of Chisel and Fertile. I was originally a Berkeley graduate student, which is when I got involved in these projects, and now I'm a software engineer at Sci5. Helping out here, we have Skylar, who's kind of doing, he manages the social media and a lot of the outreach for the Chisel and Fertile projects. So he's, I believe, I can't remember the word right now, but kind of being the admin of the chat. So hopefully he can kind of ping me if people ask questions and I'm not paying attention. Hello, and good to see you. All right, so yeah, I think there's a little bit of a latency, so it'll probably, if you send a message, I don't know how long it'll be until I respond. But yeah, I guess I'll get started. So just to clarify for those who don't know what this talk is about developing Chisel. It's about the internals, about the architecture of the system. It's not about how to use Chisel. There are other talks on our YouTube channel about that. And I gave this talk originally, I can't remember the exact date, but it was early November of 2018 at the first Chisel Community Conference. And I, that time, forgot to hit record because I apparently don't know how computers work. And so this time I hope that you can actually see what I'm doing and hear what I'm saying. So I guess might as well get started, and feel free to ask questions. I can see the chat here on my screen. So if you ask a question, I'll do my best to respond. All right, let's go. So like I said, my name is Jack Koenig. I am now a software engineer at Sci5, and I help maintain the open source Chisel and Fertile projects. I guess I need to click. Okay, so the purpose of this talk is to teach current and potential developers of Chisel or related projects about the implementation. So this talk is about the weird stuff, about what, like, maybe kind of how the sausage is made, like what's going on under the hood in Chisel. I'm assuming moderate knowledge of using Chisel and Scala. So, I will be generally, assuming that you're familiar with these things. But if you're confused, let me know, because someone else might also be. I also apologize in advance if I jump around, because this talk, there's a lot of things in here, and I want to do my best to touch on, like I said, the weird stuff, and there's a lot of interconnected things, and so I want to make sure that I cover as much as I can, and so if it's jumpy, I apologize. Please let me know when something isn't clear. All right, so from my talk yesterday, I forgot to edit my slides. So what is Chisel? So this is from a different talk that is already on the YouTube channel. Hello, Mohammed. Good to see you. So what is Chisel? It is a hardware construction language embedded in Scala. We differentiate between hardware construction, or now we're thinking about talking more about generation versus hardware description. But to clarify, it's not high-level synthesis. It's a domain-specific language where the domain is digital design. So it is a language specifically intended for designing digital systems. The way it generally works is, so Scala, for those who don't know, well, I'm assuming that you all know, but I'm going to say it anyway, is a general-purpose programming language that mixes many paradigms of programming, like functional programming, object-oriented programming, with static typing, parameterization. And so what Chisel is it provides primitives like registers, muxes, wires as objects and classes in Scala, and then we use a modern programming language, that is Scala, to productively put these components together. Like I said, Chisel is embedded in Scala, and as such, it's essentially a metaprogramming language where the actual, it's a metaprogramming language, and the actual hardware construction language and the language that you're embedded in are the same. To clarify that a bit, sorry, this is coming back to me, is that frequently when people do hardware generation in industry today, they will use Perl or Python scripts, and they essentially have some higher level abstraction, but fundamentally it's really just taking strings and concatenating them at the end of the day. It's really easy for you to have mismatches where you may have errors in your Python generator that are completely unrelated to what the types that you're actually working on, or it may construct Verilog or VHDL that isn't valid. So you may get an error in your simulator or your synthesis tool when really there was something wrong in your description. And so what we're trying to do here in Chisel is we're trying to have the language in which you describe the hardware and the hardware description language are the same, so that essentially what that really means is if you write valid Chisel, it should result in valid hardware. There shouldn't be this case where you emit Verilog that doesn't compile. And importantly, and something that I think we try to stress but maybe gets missed a lot, is that Chisel is intended as a higher level platform, or as a platform upon which to build higher level abstractions. So what does that mean? Chisel itself is not the goal. The goal are the abstractions that you can build on top of it. Sorry about that thing showing up. Okay, so next slide, if I can do it. Okay, but that is all like what Chisel is to users. What is Chisel to developers? What is it really? So it's a library of Scala classes and objects for representing hardware. We have types like uints, essence, vex, which are like vectors or arrays, bundles, which are like structs, clocks, fixed point, analog for representing bidirectional and things that we can't really handle. We have hardware itself, like registers, wires, muxes, and memories. Memories as a logical construct that corresponds roughly to SRAMs in an ASIC technology or block RAMs in an FPGA. We have structure, which are like modules. Fundamentally, if you think about hardware, a module is just an organizational unit. It doesn't actually correspond to anything in silicon. And when statements are kind of a way of helping you structure your code in such a way that maps down to muxes, but fundamentally is a structural construct. And by structure here, I don't mean structure like structural Verilog. I mean structure as in like how do you structure or organize your code. Chisel is a hardware graph. It has its own IR, intermediate representation. Now, to clarify, that's not to be confused with Churtle or Fertile, which are things that if you want to know more about, you should go watch the developer track intensive on Fertile, which is already on our YouTube channel. Chisel functions, what they do is they construct IR nodes that mutate global data structures. So we like to talk about functional programming and trying to be side effect free and all these things that are good ways to architect your software. Unfortunately, Chisel itself is not architected that way, and so we're going to kind of dig into some of that. And importantly, the Chisel IR can either be emitted to the serialized Fertile format, that textual format that some of you may be familiar with, those .fir files, and it can also be in memory converted to Churtle, which is the in-memory representation of the Fertile IR that has a couple additional constructs. So Churtle is just, it is Fertile, but with a couple more constructs that make it easier for Chisel itself to target. So I'm going to be talking about the Chisel IR, which is different from those two and lives in the Chisel repo, and you can see it there. Chisel is also a collection of usability features. We have reflective and macro naming. So we like to have the names in our Verilog match the names in our Scala, our Chisel, and we do that with reflection and macros. I'll talk more about that later. And it's also auto clone type. What is auto clone type? I'll get into that in a bit. And more than that, what is Chisel intended to be? It's intended to be a lean front end for Fertile, which means that some information may not be available. Fertile is kind of this holistic view of the circuit, the whole hardware description. Chisel is kind of this thing that runs and generates Fertile as it goes and may or may not have information about other areas of the design. So let's go through a simple example of what I mean by what Chisel is really. So here we have a register called count. Reginit, as many of you know, constructs a register that gets initialized at reset to the value here. And in this case, we assume synchronous reset because asynchronous reset hasn't been merged yet. So we have a synchronously reset register that is initialized to 0. 0.u is the literal 0. And it's an 8-bit value. So that makes sure this register is 8 bits. I then have a connection there where I add 1 to count, and that addition there is plus %, and that is truncating addition. So that's being very explicit. So addition by default is truncating. So if you write plus, it truncates. And in this case, I'm using, and so plus and plus % are the same thing. I'm just being more explicit about it. Plus ampersand is expanding addition. And so what we do is we increment count and then we connect it to itself. So when you use a register on the right-hand side, it is the current value. When you put it on the left-hand side of a connect, it is the next value, which, I guess this is supposed to be for Chisel developers, so hopefully you all know this. But now I'm going to talk about what these things actually are. So what happens when this reginit call happens? So that's calling a function. And what that function does is it creates a Chisel IR node called def_reginit, which you can see in the Chisel 3 source code. And it creates it, and it uses, count is the object reference of the thing. Clock and reset are the clock and the reset of the register. And as we know, Chisel has those implicitly in scope. So it's going to grab the actual clock and reset objects. So these are not strings, these are the actual Scala objects. And then it puts the initialization value, which was 0.u, 8.w. So it pushes this object, or creates this object that represents the Chisel IR node. Okay. Now let's look what happens when we do this addition. This addition is operating on the count to its left and the 1.u to its right. So what it does is it pushes a primitive operation, which is def_prim, and that def_prim there is adding the value on the left and the value on the right. Right, and you can see that in the seek there's count and 1.u. So those are the arguments to the add. They're on the right. Add op is the addition operator, shocker. And then _t_0. So a primitive operation corresponds to a node infertile, a node just being a named expression, if you will. And so in this case, the t_0 is the string of the name of this primitive operator. And so I hope you can see this mouse. And so, I think you can. And so what this does is, it creates a node that is _t_0 equals the addition of count 1 and 2. But that's the actual object that gets created. Now, I said it's truncating addition. So addition, as we know, expands because you can have overflow. And so we then have this tail op come in that will take that original node created, that t_0, and remove 1 bit from the head. And so this tail operation makes this a truncating addition. It's going to throw away that top bit. And then this connection is going to create a connect node, which will connect on the right-hand side the output of this addition, of this tail here, and connect it to the count. And so what have we done here? What really is happening when you see this code execute is these objects are getting pushed to this kind of global mutable data structure that is keeping track of what the Chisel is doing, right? So this code looks like it doesn't have side effects, and as far as when you're writing your Chisel, you should not be thinking about them too much, but the reality is under the hood, it's trying to construct a hardware IR, and this is what that hardware IR looks like. So in Chisel IR, these are called commands, and they're stored inside the containing module, which is called a component in the Chisel IR. And you can go see this in the Chisel 3 repo. So let's talk a little bit about types. I mentioned that Chisel is made up of types. So these types are the ways that you can represent hardware data. So the supertype of all Chisel types is called data, and it has 2 subtypes, element and aggregate. Aggregate is, as it sounds, a collection of multiple things. Element is a kind of like a leaf node, like a single bit vector. And so underneath element, we have I'll go with the simplest types first. We have bits, which is the supertype of normal types of bit vectors. And the normal types of bit vectors that you're probably familiar with are uint and essent. Those are the main 2. Uint being the standard, here's a collection of bits, it's unsigned, so we don't worry, we don't think about signed bits or anything, it's just this unsigned collection of bits. Essent is similar, except it's signed, as you might expect. and the representation of Sn is 2's complement. Fixed is for fixed point. That's an experimental feature, but it's used by the Chisel DSP people to do DSP work. And then bool is a special case of uint where, maybe if I do a pointer, it'll stop showing that. Maybe that'll go away. I don't know. Bool is a special case of uint of width 1. And importantly here, there's this other trait that bool inherits from, which is called reset. So reset is, as you might expect, the type of the input type to tell you when to reset a register. And currently, Chisel only supports synchronous reset, and bools are the input for synchronous reset, because if you think about it, synchronous reset is the same thing as a mux with an enable signal. As you all should know, Chisel currently only supports synchronous reset, but soon I'm currently working on adding another subtype here of reset called async reset, and that will allow you to have asynchronously reset registers. Under analog, we also have under element, we also have analog, which is used to represent kind of like bit vectors that Chisel doesn't understand, just to pass them through so you can connect them through your design. Those currently correspond to bidirectional things for analog and mixed signal stuff. And then clocks are, shocker, the type used to represent clocks. And you need a clock, you need to have your register associated with a certain clock, and so that's what that type is for. On the other side of data, we have aggregate. So aggregates are a collection of leaf nodes, where leaf nodes are elements. And so in aggregate, we have vex, which, as you know, are like arrays, where every single sub-element has to be the same type and the same width, which is very important. On the other side, we have records. Now, record is a name that many of you may not be familiar with, whereas you're probably more familiar with bundle. And so bundle is the main way that we represent structs, like, a heterogeneous collection of elements, whereas vec has to be homogeneous. And both record and bundle are the only data types that you can extend. And so this is where you can insert your custom types. And this is why you write classes that extend bundle. And if you're doing more advanced things, you might write classes that extend record, which is just taking bundle but getting rid of the magical reflection we use to declare the values. Okay, so jumping from types to binding, what is binding? You may see binding exceptions in your Chisel. So binding, in Chisel, the Scala type of a Chisel type and a Chisel hardware value are the same. So that sounds a little weird. So what does this mean? It means if I write val template equals uint 8.w, as far as the Scala compiler is concerned, this value here is of type uint. Similarly, I can pass this template, and I'm calling this a template because this uint 8.w, as you know, it's the abstract type of an 8-bit uint. It's not hardware. I can't connect to it. I can't do any operation on it. But what I can do is construct a wire from it. So I use this as a template type to construct a wire. And interestingly, the type of this wire is also uint, according to Scala. So if I do equality on their classes, so get class is a way for any JVM language of talking about the class, like what type an object is. So if I get the class of them, according to Scala and to the JVM, they are the same class. But fundamentally to Chisel, they're very different, because this template is just kind of this abstract notion of a uint, whereas this wire is actually hardware that we can add, we can connect to, we can do all kinds of things. And so importantly, if you try to do triple equals, which is the Chisel equality check, it's saying, in my hardware, is this thing equal to that thing? Like, is this register equal to that register, or register equal to wire, or whatever? And importantly, you're going to get an exception here, because template is not hardware. Template is a type. Wire is hardware, so if we were comparing wire to 0.u, this would be legal. But it's illegal because template is not actually hardware. And I mentioned errors, so where are errors caught? There are many places where errors could get caught. Some we like more than others. So I'm using a not surprising color coding here, where green means we like errors that are caught here. Black means it's not necessarily a bad thing. It's just a place where errors might get caught. And red is bad. So at the top level, Scala compilation is where some errors get caught. So if you try to take, my special bundle and add to it, that's not going to work because you can only add things that are bits. So the Scala compiler will tell you, and it only takes orders of seconds or less, that you can't do that. So once your Scala code compiles, so it is now compiled to Java classes that can run on the JVM, you have Chisel elaboration. So recall that your Chisel code is really a Scala program that runs and constructs the hardware. So Chisel elaboration is the running of that program. And so at this Scala runtime, there are other errors that we catch. This is kind of what I might call the Chisel type system. It's where we determine, going back a slide very quickly, it's where we determine what is the difference between template and wire. That is a Chisel elaboration or Scala runtime error. And so we'll give you a binding exception if you try to do things that aren't hardware. We'll give you a bad connection if you try and connect two bundles that don't match up their fields, so you shouldn't be connecting those things. After Chisel elaboration, we now have we have the fertile representation. So then we go to fertile compilation, where we compile from fertile down to Verilog. And so in fertile, there are certain errors that can be caught. Initialization, which I still think is probably the wrong term, but is what we use, is you have to connect to your wire under or port under every circumstance. So if you only connect under certain conditions, we call that an initialization failure. It's saying you didn't fully connect to this thing, and so there's certain circumstances where we don't know what to do. And so fertile will error. It'll error if there's a width inferencing failure, like you have some weird setup where it can't infer the width of something. Like a good example of this is if you have a top level input and you don't declare a width, we have no idea what you wanted there, so it errors. Another one is combinational loop detection. So we don't allow combinational loops in in the hardware, and so because we can't deal with it, and so fertile will error on that. A place where we don't want errors to be caught is Verilog compilation. So if you have the Verilog emitted by Chisel and you run it through VCS and you get an error, or you run it through Verilator, or you run it through synthesis and you get an error, that's bad. Please report a bug. And then the last place where errors can be caught is simulation, and those are just logical errors. You're designing hardware, and sometimes you make a mistake. You might do an and instead of an or. There's not a whole lot we can do about that, obviously. So that's where your favorite waveform viewer comes up. So briefly, some FAQ. If you look at the fertile or at the Chisel repository, you'll notice that there's multiple projects. There is the core macros, Chisel front end, and then the stuff under source main Scala, which we just call Chisel 3. Why are they in multiple projects? Because Scala macros cannot be used in the same project where they're defined. So a Scala macro, for those who aren't familiar, it's essentially a code rewriter, kind of like in C++ or C, a macro is like a thing that before compilation can generate more text, if you will. In Scala, the macros aren't quite like that. Instead, what they do is they actually can change the change the Scala AST. So a macro will let you rewrite the Scala, what the Scala program looks like. And we use Scala macros for lots of things. And so for that reason, we have to have multiple projects. I think I get into some of the macros here in a bit. Oh man, a typo that I forgot to fix as well. Another question that people frequently ask is, why do you always have project source main Scala? So you'll see core macros, source main Scala, Chisel front end, source main Scala, and then for the other one, root project, source main Scala for Chisel 3. This is inherited from Maven, not Mave. Maven, as many of you may know, is a popular Java build tool. And in Maven, it expects you to put your Java code in source main Java. And so SBT, the most common Scala build tool, although I think S now stands for simple build tool because it can also build Java code. SBT expects them in the same place. And so because it's the standard for how you build Scala code, that's why we put it there. I know, not super exciting, but that's the answer. Sorry about the typo. So now I'll talk a little bit about the Chisel project structure. As I said, we use subprojects because the Scala macro cannot be used in the same compilation unit where it's defined. So in core macros, we define a bunch of macros that are then used in Chisel front end. So the Chisel front end code gets rewritten by the core macros. And in here, Chisel front end is where the bulk of the Chisel implementation is. It's if you are digging into the internals of Chisel, that's almost always where you should be looking. The stuff in source main Scala is there's the package, which is aliases. I believe I have a slide on that in a minute, so I'll punt on that for a second. That's where the Chisel 3 util are. So things like queue, decoupled, log2up, things that you may be familiar with, all live there. Arbiter, round robin arbiter. It also has the emitter and converter. And what those do is they take the Chisel IR and convert it to Churtle for use in the Fertile compiler. There's also source test Scala, and this is where tests and examples go. Very frequently when people ask questions, hopefully there's a test showing the feature, and I usually will try and link them to something there. So this is just kind of the structure of the project. So like I said, most of the time, Chisel front end is what's the most interesting, because that's where the core of the implementation of Chisel itself exists. Skylar asked, if we're on project structure, what should be in source, main, or test resources? That's a great question, Skylar. So source, main, resources is kind of where, and source test resources. So first of all, as you probably can expect, main is where your main code goes, like the actual project you're building. Test is where the tests go for your stuff. I know that is very surprising. But I mentioned that, from Maven, we have source main Java. From SBT, there's source main Scala. There's another directory called source main resources, and it's where the way that generally works is it's additional things that go with your project. So what that usually means in a Java project is you may have some JSON configuration that is some data that you want to read in at runtime. That's not Java code. So what you would do is you would stick it in the resources directory such that when you compile your project and you make class files, or you take those class files and zip them up into a jar, the resource files get included in that jar. So for the purposes of Chisel code, the type of stuff that you might put in resources are the implementation of a black box. So if you look in the Chisel 3 util, we have this thing called has black box inline, and has black box resource. Has black box resource lets you specify a Verilog file that implements the black box that you're talking about in that Chisel code. And the normal way that you would do that is you would put the Verilog in source main resources, and then you just address it as /, and that / doesn't map to the root of the system. It maps to source main resources. And so if you look at Rocket Chip as an example, in source main resources, it has some black boxes that are throughout the design used. I hope that answered the question well. I'm going to move on, but if there's follow-on, I can always come back. All right, so talking about core macros, these are the useful macros for Chisel. How can I see how long we've been running? I don't know if I have that, but I'll just guess. Okay, so we have the macros for Chisel. So some of these are runtime deprecated. What that lets us do, so in Scala, there's already a deprecated macro, @deprecated, and when you mark something with @deprecated, then the Scala compiler will give a warning for it. The problem is that people frequently don't have that warning turned on. I don't know why it's not turned on by default, but it's not. So we added our own thing to make sure that people see this, called runtime deprecated, and this is at the end of Chisel elaboration. We print a really annoying message that many of you are probably familiar with that tells you that you use deprecated functions and tells you which ones you used and how many times you used it. We have the range transform, which is this really neat thing where it can take a string representation of a range, and what that means is if I write, does it work? No. Maybe I can turn on a writer. No, I just have a pointer. Okay, well, if you can have a range from 0 to 10, inclusive or exclusive, and this will map to an interval type. Interval types are not really part of core Chisel yet. They're still an experimental feature, but that's one of the macros that lives there. Chisel name is a really good thing for giving us names beyond reflective naming, and I'll talk more about that later. And then source info transform. Despite the name of it, this actually does not provide source locators, which is very funny and very surprising to people sometimes when they're trying to debug it. What it actually does is it allows for chaining apply, which is bit extraction when you use it on chisel types, after you call a chisel function. I'm going to talk more about that later because that's kind of a subtle issue. And it's a little bit odd, and it results in a lot of the source code of Chisel looking strange. And so it's a very important thing that I'll talk about in a minute. Okay, now the Chisel frontend. As mentioned before, this is in Chisel frontend source main Scala. It has two subdirectories, internal and core. The internal directory has the builder. The builder is the thing that holds all of the internal mutable state that Chisel is utilizing as it runs. This is where I talk about pushing, those Chisel IR nodes. This is where they get stored. It also has fertile IR, and ironically that is not fertile, that is the Chisel IR. And so that's where you'll find the descriptions of the Chisel IR nodes. Now, the reason why it's called fertile is really historic, and it's because it's very similar to fertile. The IR that it's building there is very, very similar, but it's not exactly the same. And so I'm going to call it Chisel IR. And here is where you have source info. And this is the actual thing that creates source locators. Now, why is this defined? And this is also a macro, I believe. It's a macro and a materializer. A materializer is just a way to tell the Scala compiler that if no instance of this is provided, create one. There's no reason why most users would want to create their own source infos, but you can imagine a library that wants to lie about the source locator, like an advanced diplomacy in Rocketship might want to give you source locators from the user code rather than from the diplomacy source code. And so it's conceivable that they could create the source locators themselves. They actually don't do that currently, but it's possible. But the materializer, what that does is it inspects your Scala source and can actually determine the line that it's on. And that's how we provide you source locators in the Verilog. So the source info creates your source locators. And we defined it in Chisel frontend instead of in core macros because of this. We want it to prevent creation of source locators in Chisel frontend. If we did this differently, you might accidentally end up with source locators that are the Chisel source code itself, and that is not what you want. You don't want something to say bits.scala as the source locator when really it's mycoolproject.scala. So that's why it's defined there. And then we also have core. And what's in core is where all the user-facing Chisel classes and objects are created. That's where module and data and wire and when and printf are all defined. So if you're looking for the implementation of those things, you should be looking at Chisel frontend, source main Scala, core. And this is definitely where I spend most of my time when I'm working on Chisel. It also has the compile options. For those who don't know what those are, we have this we call it the compatibility mode, which is really, it's kind of this, we call it Chisel 2 compatibility, but that's really not right. It's kind of this Chisel 2.9 intermediate between Chisel 2 and Chisel 3. And the compile options allow us to determine where source code is defined, where if you write plus, is that defined in something that's written import capital Chisel, which is the compatibility mode, or is it import lowercase Chisel 3, which is what newer code should be? And this lets us distinguish between those. So based on your source code, we can determine how strict our checks should be, is what that does. And then last but not least, we have Chisel 3. This is what's in source main Scala. This is where the driver exists. So if you've ever written driver.execute, driver.elaborate, driver.emit Verilog, that all is in there. It's where package.scala is, and that's where if you write import chisel3._, that's pulling everything from inside package.scala. Now I believe that this might be changing in Chisel 3.2, but this is how it is and how it's been for years. So we have package Chisel 3, or package object Chisel 3, and inside of there is where when you import chisel3._, all the things in there come from. Compatibility.scala is where the import capital chisel._ stuff comes from, which is why it can be slightly different. We have the util, where common utilities live, like decoupled, queue, arbiter, log2seal. I said log2up, but log2seal is a safer thing to use. And then, as I mentioned before, we have the emitter, which emits the serialized representation of fertile, those .f files, and the converter, which is an in-memory translation from Chisel IR to fertile Fertle's actual IR nodes in Scala. And I'd just like to reiterate, if you have any questions, please feel free to ask. I hope this isn't too much like a lecture. When I originally gave this talk, it was very back and forth, so sometimes it gets lonely talking to myself. So a word on package.scala. Why does this exist? So in Scala, all defs and vals must be defined inside of an object or class. And so this lets us define all the defs and vals that are included in import chisel3._. Why is this useful? This lets us rename things. So I actually don't know if this is still true, but it used to be in chisel3.core, the thing called legacy module is the thing that you instantiate when you refer to module. So if I have class my module extends module, it's actually an instance of chisel3core.legacy module, but this type aliasing here, so this type alias refers to the class, this val alias refers to the object, the singleton object, chisel3core module. And so it allows us to rename things. And what's nice about it is it allows things that may be in different packages to all be imported with one fell, import chisel3._. It seems like this might be providing more confusion than it's worth, and so I think we're talking about getting rid of it, but this is, like I said, how it's been. So a little bit more about the driver. It's the user API for invoking Chisel. So, you can define Chisel classes and objects, but if you actually want to elaborate them and get hardware out, you have to invoke it through the driver. So it has a main for the command line interface, which is a little tricky to use considering you need to instantiate a Scala object. It has execute, which is what's called by main, and this invokes Fertle in the same JVM. So this is convenient if you're trying to just run Chisel and Fertle, but if you need to break it down, like what Rocketship does, where it emits the .fir file and then actually compiles it, invokes Fertle in a separate JVM. They don't use execute, but that's something you can use. Elaborate allows you to just invoke Chisel and get Chisel IR, not Fertle. Emit lets you invoke Chisel on a module and get the emitted Fertle, so this will give you the text of the Fertle. Sorry, I can't see what's underneath it. There's also dump Fertle, which will call emit and dump that Fertle to a file. And then there's dump proto. And I haven't really talked about the protobuf stuff, but for those who don't know, protobuf is a serialization format from Google, an open source serialization deserialization format from Google. It's kind of similar to what people usually use JSON for, where you can serialize and deserialize JSON. But I chose protobuf for this instead, or we as a group collectively decided that it was the right move, because protobuf has some nice properties, like it is very fast, although many JSON things are fast these days. But it already, it has kind of like a version, it has, what's the term? In JSON, for those who've used that, I'll talk about that in a second, Skylar, but good question. So frequently when you have JSON formats, as you evolve a format, you have to have a schema, which is like, what version of the schema is this JSON? This is for forwards and backwards compatibility. So one thing that's really nice about protobuf, and I would actually encourage people to look at it if you need some serialization format to communicate between two pieces of code, is it builds the schema into the description of your data structure. And it doesn't quite enforce forward and backwards compatibility, but it makes it really easy to do, if that makes sense. And so we chose protobuf because it's a really common format, it's very fast, and it's well supported in many languages. I mean, it has Java, C++, Python, Go, like most languages you can think of have a protobuf implementation. So Skylar asks, Jack, how much faster is protobuf? So this is kind of an interesting question. So the reason why you may wonder why not just use the the Fertle serialization format. You already have a serialization format. Why add another one? So we've had this long-standing issue in the parser in Fertle. So we use Antler, which is a Elixir parser generator, and it's a great tool, by the way. I really like Antler. It has many language support for a lot of languages. It also supports left recursion, which because it can transform it into something that's still optimal. And so It's a really good tool for parsers if you need one. But the problem is we couldn't, and there is probably a solution to this that we couldn't find, but the antler emitted parser in Fertile has really nasty performance cliffs where it will just use tons and tons of memory. So we have a very large design here at Sci5 that in memory in Fertile is something like 2 gigabytes, which is already massive. You're a 2 gigabyte design, are you kidding me? And it actually might even be 4 gigabytes. But when we used the antler parser, it was hitting 64 gigabytes of memory. And if it didn't have 64 gigabytes of memory, it couldn't parse it. And so to answer Skylar's question, how much faster is protobuf? Well, allocating memory and garbage collecting memory is time. And so whenever I managed to get the protobuf part working for that particular design, instead of using 64 gigabytes, it was only using like 7 or 6 to do the full parse. And it ran, I don't remember how much faster, but it was at least 10x, and it might have been more than that. I'd have to go back on GitHub and see, but it was insane. For small designs, it doesn't matter, and we still use the Fertile parser for a lot of stuff, but if you have a really, really large design, actually I can tell you what design this was. This was the, what is it called? The Hi5 Unleashed. If you go look at that board, the Sci5 Linux running, I think it's 5-core design, it was taking 64 gigabytes, and it was just ridiculous. So that's fixed by using protobuf. Next slide. Okay, talking about the builder a bit. So the builder, like I said, is kind of the internal mutable state. Another way to think about that is it's like the internal runtime. It's like, where does Chisel keep all of its information? It's the entry point for Chisel elaboration privately. Obviously, publicly you go to the driver, but privately the driver just calls the builder. And it has the interface for calls into the dynamic context and the Chisel context. So what are these things? They are the objects that hold global mutable state during elaboration. They're wrapped up in Scala util dynamic variables, which makes it to where they're global state that is thread local. So that's important if anyone's interested in how would you make Chisel parallel. You have to keep in mind that currently the way that we synchronize this data is thread local, which is nice because at least Chisel is you can run multiple instances of Chisel and it won't cause a problem, but it is still global state, and so we have to share it somehow, and we share it through these thread local data structures. Like I said, it imagines multiple invocations of single-threaded Chisel. All calls that mutate global state go through the builder. So every time you do an addition, it needs to push that addition node into the global state, and it pushes it, push op is the way that happens, and it puts it into the builder. Anything that asks for the current module needs to find out what is the current module that's being elaborated. That information is also stored in the builder. So whenever if you are developing on Chisel and you're what happens whenever someone says if for those there's a call that you can do called module.clock, and I want to clarify that's not the same thing as asking for the clock field of a module itself. That's object module.clock. And that's a way of getting whatever the currently in scope clock is. And so that call goes into the builder, finds out what the current clock is, and then returns it. So anything that requires that global state. What's in the dynamic context? So I mentioned on the previous slide the dynamic context and the Chisel context. Let's talk about those. So what is the dynamic context? This is all the Chisel elaboration global state. It's where the namespace is. How do we name modules? We have to make sure they don't collide with each other. Where do we store those modules as they get elaborated? Those are called the components. Where do we store annotations for whenever you're trying to annotate something with additional metadata? We have annotations. What is the current module? An interesting one here is the ready for module construction. So what this allows us to do, as most of you probably know, you have to, if you construct a module object, you must wrap it in module open parentheses, close parentheses. What this lets us do is detect when people mess that up. You may have no wrapping, you may have multiple wrappings. You may have module open parentheses, new my module, close parentheses, close parentheses. You might also rewrap an object. So this global variable lets us figure that out. The win depth allows us to know the depth of nesting for wins. This is important for how we, because I mentioned that Chisel is a very lean front end. So whenever you have a win, it just pushes something. It's not actually really constructing nested scopes in the commands. The commands being, like I said earlier, the Chisel IR nodes. So the win depth, what that lets us do is keep track of how deep in wins we are so that when we exit them, we know basically how many closing curly braces to insert. In Fertile, the serialized form, there aren't curly braces. It's white space scopes, but it's kind of like how much white space scoping do we need? The current clock and reset, this is actually about to change to current clock and then a separate value for current reset to fix a bug. But that is, what are the currently in scope clocks and resets when you construct a register? Errors are the error logs. So for errors that are not fatal, we try and record them as we go and report them all at the end. Those get stored in the error log. And then the naming stack is utilized by the Chisel name macro that I haven't gotten to yet. So what is the Chisel context? This is the global mutable state that can appear outside of Chisel elaboration. So this allows you to instantiate Chisel types like uint or bundles outside of Chisel. It used to be if you tried to write uint, 0.u, it was an error because you weren't in Chisel. But as you might expect, that's really useful for like Chisel tester and for things like that. If you want to test your Chisel code, you still want to be able to create Chisel types. And so outside of it, we have a Chisel context, which allows you to keep track of that type of stuff. Interesting, and this is where a thing called the bundle stack lives. Do I have a slide on that? I don't know if I have a slide on that, but the bundle stack is something really fun. This is probably the grossest thing in Chisel, where in order to do autoclone type, I think I talk about this later, so I'm going to punt on it, but this one's fun, so buckle in. The compile options, as I mentioned, they allow us to enable Chisel 2 like semantics within Chisel 3 code, and so we implicitly create these objects and pass them to every Chisel function call, and that allows us to be less strict about code that is using the older Chisel semantics. And kind of neat, it's possible to mix and match these options. You probably shouldn't very often because it will likely go wrong, but it's something you can do. You can do it explicitly. So any code that's import capital Chisel __ is using explicit compile options, not strict. And if you want examples of like how this stuff works more explicitly, because this is kind of all done magically, you can see source test Scala Chisel test compile options test kind of illustrates what's actually going on. All right, source locators. So I mentioned that we have the source info transform, which does not make the source locators. So what does it actually do? If you look at bits.scala, which is in the Chisel front end, source main Scala core, you'll see final def plus that t. So this allows you to add 2 uints, or 2 bits. And then it has this weird thing, macro source info transform that arg. And you're kind of like, what the hell is that? What that is that source info transform that's defined in core macros, as it says up here, has a thing called that arg. And what it does is everywhere in your source code that you see a plus, that you are calling this function, it replaces it. It rewrites your code to say do +, the same that you were adding, and then it adds 2 implicit arguments. These implicit arguments are the source info, that source locator that I mentioned, and the compile options. Now, for those who know a little bit more about how implicits in Scala work, which I'm going to suspect that most of you don't, but it turns out that we don't actually need the source info mac transform. We could have instead said final def plus, that t, and then take this whole implicit argument list and stick it right there. If we did that, source locators would work just as well as they do today. So why do we need this whole macro that takes every plus and replaces it with do _+? Well, what happens if you wanted to chain a bit extract after a plus? If I wrote my wire +1, so let's imagine that we had the other plus, like instead there's no do plus here, pretend like this whole argument list is actually up here. If I wrote my wire +1.u and then tried to extract bit 1, you're going to get a compiler error in Scala because this looks like a second argument list to this function. So for those who know, or for those who don't know, mywire plus 1.u is the same thing as writing mywire dot plus, like it's a method defined on mywire, and passing this argument. So then this looks like I'm trying to pass a second argument list, and it's going to see that attempted second argument list and say, ha, you could be passing implicits, so you must have been trying to pass the implicits, this is a compiler error. But really that's not what you want. In Chisel, when you write this, what you're trying to say is add these numbers and then extract a bit. And so what this macro does is it allows you to write this, which is the same thing as this, and then the macro says, I see this part here. This is clearly not trying to pass these implicits. This is clearly calling dot apply. Do I have a slide that does that? No, I should have done that. This is clearly trying to do a bit extract. I see that these implicits are necessary. Because they're implicits, I know how to go materialize them, and it's going to inject an extra argument list right here. So what this really looks like is my wire dot do underscore plus 1.u gives it a source locator, gives it compile options, and then now let's extract bit 1. Like I said, I should have made this slide a little better, but the whole point of the source info transform macro is really just to let you do a bit extract after you do a Chisel operation. And it's like, for those who've looked at the Chisel source code, you'll see all these do underscores and you see all this work, and literally it's all for that. That's all it's for. And so you can thank Richard for doing all that work. It was great stuff, and it allows you to write Chisel that looks really simple and awesome, and under the hood, we're doing a lot of work for you. We're giving you source locators. We're allowing us to support older semantics of Chisel, and all of this at the same time. All right, now let's talk a bit about reflected naming. So maybe instead of recall, I'm just going to talk about this. The body of a Scala class is the primary constructor. That is, it is the code that is executed when you construct that object. There are ways to create other constructors, but that's an uncommon pattern in Scala. So my module here it extends module. This is a class. So this here is the body of that class constructor. Now in Scala, sorry, I'm going to take a drink of water real quick. In Scala, vals are public fields of the class. So even though this is the default constructor, these fields are also like members of the class. And so anyway, they get constructed. These get created whenever this module first gets instantiated, this object. But importantly, when we name by reflection, we can only name the public fields of the object itself. So, like I said, the body here are the public fields. Sorry, these vals and these defs are the public members of the class. So if you think about Java or C++, it's like when you declare a public int or whatever. So these are known to the JVM as the members of the class. Okay. And so what is Java reflection? Reflection is this larger programming construct where a program can introspect, it can reflect on itself. You think about it looks in the mirror and says, I know what I am, I'm a module. And so by using Java reflection, we can inspect the public fields of the class, and we can say, I see, you have this val.io, I know the name of it, the name of the field in Java and Scala is io, I can name that. And so what Chisel is able to do is introspect on this thing and see that we have a thing called io and a thing called wire. And that's how we're able to propagate those names into the Verilog. However, if you define things inside of a function, so this function is a member of the class, but this field, this val reg, is not. So how can I name this reg? It's not possible via Java reflection. If it were possible, we would have done it. So as most of you who've written Chisel know, if you wrote this code, that reg is going to be named _t_garbage, right? And it's really annoying. You're like, well, I called it reg. Why can't you know that it's a reg or that it's named reg? So this is where we have this macro called Chisel name. So I talk about macros. Macros are things that rewrite your code. Those macros I showed before, like the source info transform and source info, those are called def macros, which can rewrite a function and they don't require any changes to your source code. That's what's really neat about them. This is called a macro annotation. And by annotating this class with the macro annotation chisel name, there is some code in Chisel that will go in here, look at the Scala AST and rewrite it. And so by inspecting the Scala AST, as opposed to the runtime Java representation, the JVM representation, there's a lot of information lost once you've compiled to Java bytecode. But in Scala, we have the entire AST. And so this macro lets us look at this AST and say, I see you have a val that is a register, and you called it reg. I'm going to name this now. And what it actually does, I didn't keep this here, but there's this function we have called suggest name, and it will call dot. What it does is it rewrites this code to have dot suggest name on this reg. And now the register will get named reg. And that's pretty neat, I think. That's another thing that Richard implemented, so kudos to him there. And so if you find yourself with a lot of scopes like this, anytime you write a curly brace, that's a scope. So if it's inside of a for loop or inside of a function or whatever, it's a good idea to use chisel name because then we can still name your vals. Widths. So because Chisel's a lean front end, wow, typo galore here. Because Chisel is a lean front end on Fertile, not on Chisel, on Fertile, widths are often not known to Chisel. And the way this is almost always phrased, and I get this a lot as, kind of supporting the engineers here at Sci5, is why is .getWidth failing? It worked, and all I changed was this one small thing. So here's some examples. Val x equals io.n. Why did I not define io.n? Okay, that's weird. Let's assume that io.n is an 8-bit UN. So if I write, I see we have a question. Could mandating a similar sort of an annotation eliminate the need for source info transforms? That is a great question. I'm actually not sure about that. It's possible. It's possible that we could, instead of having the source info transform and have all those do underscores, just have the macro define everything. I suspect that the way the errors will work if you forget the annotation will be really ugly, but it's definitely worth considering something like that. If you had like a compiler plugin so that we could inject our own errors into Scala compilation, we could maybe require a macro and then error if you don't include it, and therefore the errors messages would be a lot better. But fundamentally, unless we're going to do modifications to Scala itself, which could be done via a plugin, but still, like if we're going to inject ourselves into the Scala compiler, the error messages you're going to get are pretty nasty. It is true that Paradise is packaged in 2.13, but that wouldn't change our ability to inject our error messages. So what Paradise is, for those who don't know, is it is the implementation of macros in Scala is not included by default. It's a compiler plugin. And Chisel includes that compiler plugin. But Paradise itself only gives us the ability to write these macros. We would have to write our own thing, kind of like Paradise, in order to give our own error messages for things like that. But that's a good point. I mean, that actually might be worth exploring. I've thought about trying to write a plugin before because certain errors that you get are really hard for new people, and it would be nice if we could give suggestions about what they should look at, but we can't because it's the Scala compiler. So, great question. Okay, so sorry, back to widths. Yeah, sorry there's a bit of a delay, so sometimes it takes me a second to see questions. So right, we're assuming that io.n is an 8-bit UN. And so if I multiply io.n by itself, well, because the width is known to Chisel, we know that the output is 16 bits. If I then took this known to be 16-bit x and multiply it together, we now know that y is 32 bits. But what if I write val z equals y or uint, open parentheses, close parentheses, and that means a uint of undefined width, it will be inferred. And I type, let's connect z to y times y. Why is this an exception? Well, because of the way width inference works, I know there's only one connection here to z, and you're saying, well, it's obviously 32 bits, but what if below this print, someone wrote connect z to some 128-bit value? So we can't know the width of z because we can't possibly run width inference here. And like I said, it's simply not possible because there could be a connection later that that print line doesn't know about. So the most common example of when get width was working and then starts failing is somebody injects a wire like this and then connects to it and expects the widths to be known. Another common question is, why do we have to wrap modules in module? This is because we need to insert hooks before and after module construction. An example of that is we need to be able to set and unset the current module. Why do we need it to, in that current module, as I mentioned earlier in the discussion of builder and the dynamic context, is this global mutable state. So why do we have to set that? What if someone wrote object foo def add one x un, x plus 1? There is nothing in that code there that tells you what module we're adding to. So if x, the UN, knew what module it lived in, then we could do it. But somebody has to know what the module is. And so the way it works is when you do this addition, that plus there will go and check the global state to see what the current module is, and then push this IR node into that module. It'll say, I have this addition of x with 1 inside of that module. And so, like I said, that's why we have to wrap modules in module, because we need a hook before and after construction. If you look at object module method apply, you can see the code that we run before and the code that we run after. Earlier, I talked about how bundle extends record, and some of you may know what record is, but some of you may not. What are they? A bundle is kind of like a struct. It's just trying to let you put heterogeneous data into a, some structure. The record is a superclass of bundle, and the difference is that rather than, so I'm going to use this bundle down here as an example. When you write class myBundle val foo equals un8.w, earlier I mentioned that we use reflection to determine names. We also use reflection to determine what the fields are of the bundle. So the reason why we know that bundle has foo in it is that we can inspect the class. Oh wow, I forgot to extend bundle here. Shame on me. So if you wrote this won't do anything. It will not be a bundle. But class myBundle extends bundle. Then we can inspect the body of this bundle and see that it has val foo and know that that is the only element of this bundle. And so records are the superclass of bundle, and they have this field called elements, which is a list map. A list map is just a map that has defined order. We need defined order for determinism. You obviously, well, not just determinism. It's really important that we keep the order of the fields in your bundle, because some of them, if you cast it to a uint, are the high order bits, right? That's like really important. Like, what are the order of the bits in the bundle? And so that order matters. And so we have to have a map that has defined order. Now, there are problems with list map, and you may see that there are open issues about this. We really need to get this fixed. There's performance problems because list map has a linear lookup, but forget about that right now. But the idea here is that bundles automatically can populate elements. We use reflection to say elements is a list map of size 1 with foo to this uint8. We're reiterating the question about annotations that can eliminate wrappers. The question is, I'm tempted to reiterate my question, would it be possible to devise a magical annotation that could eliminate the module or even wire wrappers? Ergonomics is a huge concern for many new chiselers. That's a great question. I am not sure, to be honest. It's definitely possible with macros to not require those wrappers because we could inject them ourselves. And then he added, or even for autoclone type, I think autoclone type is the next slide. So I'll pause on that one for a minute. It is definitely possible that macros could be used to implement these wrappers. It may or may not be a good idea. As you mentioned, it can be confusing. Why do I need to have these wrappers? And so that's a reason why you wouldn't want them. One reason why you would want them is it does help you distinguish between things. If you write uint8.w, that's not a wire. You need to tell it that that's a wire. So in that case, you would need to wrap it anyway. But for module, like you said, we don't need to wrap module. If you wrote new my module, we know what you're doing. Like, it's not really that helpful to the user. Those are great questions. I think that those are things that you should take to the entire group of developers. We have our developer meeting at noon on Fridays, noon Pacific time. And you can, of course, ask that question as an issue on Chisel. I think, Skylar added, more so for me is that I was confused for a long time as the module object and the module class are very different. I mean, these are really great questions. It's, how do we communicate to people? Some of these things are patterns drawn from Scala, and a lot of people are new to Scala. So it's very confusing if you're coming from Verilog and you're like, what the hell is module open parentheses, why can I extend module and also do that weird thing? Yes, it is an online meeting. Skylar, if you could you put a link to, Chisel Dev? I think the Chisel Dev mailing list sends out a reminder every week. So if you could link to that, that would be really helpful. Right. I'm going to, so for these questions that are very good questions, I can try to come back to them at the end. I'm going to move on for now, but I think these are things that we should talk about in the larger developer context. All right, so like I said, record is a superclass of bundle, and all records require to have a list map of elements. Bundles are a special case of record where we can automatically generate that list using reflection for what the elements of that bundle are, which is kind of neat. But records require you, if you use record, it's allowed you to be programmatic. So as you can see, if you look at class my bundle val foo, that means any instance of this bundle has foo. What if I want it to be programmatic? Like, depending on my input data, I may decide what the fields are going to be. That's what record's for. And record will require you to implement clone type and elements. I talked about elements already. Now I'm going to move on. I think the next slide is about clone type. Yes, good. So what is clone type? What and why? So because Chisel types are immutable objects at runtime, and that because makes it sound like this is like a restriction, but this is an intentional design decision. We need to be able to create fresh clones of them in order to create hardware or add a direction or something. Right? So looking at this val IO new bundle, open curly brace, in here I have uint8.w. Now uint8.w, like I mentioned, is the kind of the abstract notion of an 8-bit uint. But I also need the ability to add the direction input to that. So I can't mutate this object, because if I mute down here below, you'll see why it wouldn't work. So let's just hop down here, actually. If I write val gen equals new bundle, open curly brace, val foo, input uint8.w, I have an object here that is an instance of this bundle. This bundle has a field called foo. That field foo is the abstract notion of an 8-bit uint that has the input direction. Okay, that's what gen is. But I can't mutate this object, because what if I pass gen to IO? This constructs IO as a new object. It's not the same object as gen. And IO is gen, but now we took that and said this type here, this abstract type, is now the hardware IO of this module. So I have now constructed a port. That port is an aggregate type, a bundle with a single field in it. I can also construct a wire of the same type. So I can pass gen to wire, and then that lets me get val w. And W and IO can be connected with this bolt connection. So because of that, we need the ability to take some Chisel data object and create a fresh clone of it. And that's the function that we call clone type. And that's why when you get an error sometimes, it's because Chisel has to be able to determine how to create new clones of your thing. For those who are not as into immutability and functional programming, this notion here that these are immutable and that I need gen and IO to be different objects is the concept called referential transparency. And while I mentioned earlier that Chisel is this kind of ugly mutable global state thing that's gross. We try very, very hard to present to the user a functionally pure-ish and side effect free and referentially transparent world. And it's really compelling that passing gen to IO, like this just works, and it always works. If you're doing things like this in C++ or Java in a language that is less immutable, it's really hard to determine when do I need to call copy. Should I call gen.copy here, or should I call copy here, or where are things copied? And under the hood, we handle that with clone type. But as far as the user-facing API is, you know, we handle all that for you. So, like I said, clone type is this implementation detail for how we get a fresh copy of something. For everything internal, we obviously have an implementation of it. Like uint has an implementation. Nobody has to ever worry about that. But for user bundles and records, where you created your own custom data, we have to have an ability to clone it. Normally, this is very formulaic, right? If I have class my bundle, so for those of you who've been with Chisel for a long time, like Chisel 2 and early Chisel 3 before auto clone type, this is what your bundle had to look like. You had to write class my bundle, and you had some width. You know, like I want to parameterize my bundle by the width. That's a really common thing. And I have my field, and it's a uint of that width. The problem was we didn't know how to construct a new bundle, so you had to create, you know, override def clone type colon this dot type. This is a really ugly thing that I don't really want to get into. This is, I think it's called the existential type or something like that. No, the self type. And this is a special type that is the type for only this object, not this class. This dot type is different for different instances of my bundle. And that's a really weird concept and it's hard to wrap your head around. And it's really annoying that you had to write override def clone type, this dot type, new my bundle, pass the width, as instance of this dot type. If you look at this, this is so obvious. Obviously, if I'm trying to create a clone of an object of my bundle, I just want to create a new my bundle with the same argument. Like, duh. And in some languages, like a shout out to Python, which despite being, you know, I'm a big Scala fan, I'm not a huge Python fan, but in Python this is really easy to do because they have duck typing and all these things. In strongly typed languages, this is actually really hard to do, and that's why for a long time all Chisel code had this in it. Enter auto clone type. This really cool, I like to call it a beautiful reflection masterpiece, because it is kind of amazing in how well it works and kind of horrifying if you ever peek under the hood. What it does is it automatically collects all arguments to the constructor, the default constructor, but that's normally the only way you do this stuff, and it constructs new instances with them. Now, in order to be able to do this reflectively, the arguments must be vowels. So that's why instead of width int, so I'm going to go back really here for a note on Scala. If I have an argument to a class constructor with int, this here is not a field of the class. This is only an argument to the function, the default constructor function. So it's not even a private field. This does not create a field in the class. It's only an argument to a function. Whereas if you put this val here, it is an argument to the function, but it is also now a public field of the class. Which means if I have an instance of my bundle, I can do .width on it and it will return this value now. So in order to do this reflection masterpiece, if you make your arguments vowels, and the error message will tell you to do that, we can reflectively find these vowels and create that clone type function for you, which is pretty cool. But what about inner classes? What is an inner class? In Scala, you can have class my module, and inside of it, class my bundle. And importantly, the type, this is a concept known as path-dependent types. It's not common. Not that many languages have it. It's mainly a functional programming language kind of thing. Like if you're familiar with Koenig, which is like a very proof-based and formal reasoning language, they have it. But Scala is actually in the minority here. But it's a very powerful concept. What it lets you do is it lets you describe a type here that is dependent on the instance of the outer class. So the type my bundle depends on a particular object of my module. Now that's not that useful here. In this case, It's not doing anything special with it, but there are some very powerful things you can do with this construct. But the issue here is that while it's not specified here, the instance of the outer class is an argument to the constructor of the inner class. So the object of my module, the particular object, is used as an argument when constructing my bundle. Okay? Now normally Scala reflection, so there's Java reflection, which is the reflection built into the JVM. There's also Scala reflection, which are additional functions that Scala can generate for you. Scala can provide the outer object. So when I write my code like this, secretly in here, you can't see it, but there's a way to find out what object there is of my module that corresponds to my bundle. And that's important because, like I said on the previous slide, AutoCloneType needs to collect all the arguments to the constructor and use them to call that constructor again with those arguments, right? It needs to call new my bundle and pass it this width. So for my bundle here, it needs to call this constructor. Notice I put no arguments here, but there is actually an argument. It's the instance of my module. So when it tries to call the constructor, it needs the object of the outer module in order to construct the bundle. So, like I said, Scala reflection only provides this object. Oh yeah, I did a lot of explaining, but I actually gave code here. So this previous code here, this is what you actually write in Scala, but what Scala does under the hood is it generates something that looks kind of like this. This here is called the self type. It's a way of getting a reference to an object. It's the same thing as writing this, if that makes sense. There's reasons why it's useful, but I could have similarly just written this right here, and that refers to the instance of my module. But implicitly under the hood, my bundle has an argument that is an instance of my module. And this is what the code actually looks like. Okay? Like I said, normally that outer object that is available by Scala reflection. For some reason, I don't know why, Scala does not do this for anonymous inner classes. So if you have an inner class that doesn't have a name, like this one, new my bundle open curly brace, I maybe should have explained this a bit earlier, but for those who don't know, what this syntax is, bundle is an abstract class. You can't instantiate abstract classes, but what you can do is create an anonymous class, an object of an anonymous class. So when I write new bundle open curly brace, I have created a new class that has no name with a field in it called field, and there's only one instance of that object, of that class, and it gets constructed right here. But like I said earlier, this is an anonymous class, but we still need it's a single object of an anonymous class, but we still need to be able to create new instances of that class. And annoyingly, Scala doesn't know about the outer object here. I suspect there are reasons for this that are implementation. I don't know what they are. But Chisel does know what the current module is. So when it sees this code, when it has this bundle object that we know takes an argument, because it's an inner class, we can guess that the object is the current module. So when we try and clone this bundle, what we do is we just guess, is it my module? And the answer in this case is yes. And that's pretty cool. So despite the fact that Scala is not helping us out, we can just try things and see if they work. But what happens, so in that case, I have an anonymous bundle inside of a module, so I can just guess the current module. What happens if I have a bundle inside of a bundle? How can I possibly get a reference to this bundle? Well, I talked earlier about having pre and post hooks. The reason why we have this module wrap is so that we can set the current module and then unset it. That pre and post hook allows us to always know what the current module is. We don't have any such functionality for the current bundle. So the way we do it is every single time you construct a bundle, we collect a stack trace and then we can compare the stack traces. So going back a slide, when you construct this outer bundle, it creates a stack trace. when you construct this inner bundle, it creates a stack trace and then relates it to the other stack trace and can see that this construction is occurring inside of this other function invocation. And yeah, it's pretty messy, but it works. And so via that stack trace collecting mechanism, we are able to determine, and this isn't even a guess, it's a guess, but it's a pretty well-educated guess. We know what bundle your anonymous inner class is defined inside. So like I said, this is kind of amazing, but it's a total mess at the same time. This is something that there are probably somewhat better ways to do it that are not, I say better, there are somewhat faster ways to do it because stack tracing is a bit dangerous, or not dangerous, sorry, is a bit expensive. But, the stack traces work really well. And the mastermind behind this is also Richard. So Richard has done a lot of the really cool, nasty, yet incredibly functionally useful things. He did chisel name, he did auto clone type, which is this, and he also did the source info macros in order to let us, get your source locators and also allow you to do bit extraction immediately afterward. So kudos to Richard. You should tell him how awesome some of his stuff is because all of this works because of his hard work. Yeah. All that. What fun. And then I think this is actually my last slide here. Skylar put in a little duck emoji because, as many of you know, Richard frequently uses the username Ducky. I think Ducky64 or something is his GitHub username. So sometimes he goes by Ducky. He did all that work. I'm going to talk a little bit here because some of the developers like to use IntelliJ and it's kind of hard to get set up. I think these tips are on the Chisel 3 wiki, but if they're not, they really should be. So I'll check that after we're done here. But it can be useful for developing Chisel to use an IDE like IntelliJ because it allows you to single step. It allows you to really see what's going on. Because Chisel has so much mutation and global state going on, it can be hard to trace what goes where. And so whenever I have really hard bugs, I will switch to IntelliJ. I'm mainly a Vim Bash user myself, but for Chisel development itself, sometimes I do use IntelliJ. And IntelliJ is getting better and better for Scala, so I'm hoping eventually to make it easy to, many people are like, want to use IntelliJ with Rocketship, and that's really hard to do. But someday, I'm doing some work right now that might help with that. So some tips if you want to use IntelliJ, you need to run sbt compile on the command line before you load the project in IntelliJ. And the reason for that, and this is very confusing and doesn't make sense, but it actually has a very simple explanation. It's confusing if you don't know what I have finally figured out. IntelliJ projects, so what happens is when you export a project from SBT to IntelliJ, they're completely different descriptions of the project. So IntelliJ doesn't call SBT. It does only to export the project, but it doesn't really, it kind of is getting there, but it doesn't really use SBT as the builder. Historically, IntelliJ has its own description of the build, and SBT generates like the metadata, like maybe, I think it's a JSON file for that description. And so once you export it, it's now IntelliJ's problem. And IntelliJ didn't support code generation. So whereas SBT for Fertile has an Antler plugin, and that Antler plugin knows how to generate code, and there's a dependency on the generated code that generated Java code and compiling the rest of the Scala code. IntelliJ didn't understand that concept, and you had to use plugins. And so it didn't really work that you could go from SBT and Antler to use IntelliJ's Antler plugin. Like that mapping doesn't exist. And so if you have any code generation, and we have several examples, in Fertile, we have Antler and Protobuf, which generate Java code. In Chisel, we have build info, which generates information about the build, like what is the version of Chisel that we're talking about here? What is the version of Scala we're using? What is the version of SBT? Any code generation needs to be run before you create the IntelliJ project. And so that's why the tip is run SBT compile on the command line, and then you can open it in IntelliJ. Now, if you modify any of these files, the build info description, the Antler description, or the Protobuf description, then you need to rerun it on the command line. All of this is getting better. The Scala world over the last about year and a half has been investing heavily in tools. There's this new tool called Bloop that's really cool, and they have this thing called the Scala build server protocol. And so pretty soon, I believe IntelliJ, not the released the IntelliJ Scala plugin, not the released version, but the like nightly build version, supports using the Scala build server protocol, and then therefore can use SBT or Bloop to do the rest of the work instead of doing it itself. So someday soon, these caveats might not be true, but today they are. And I think that's my last slide. Yeah. And it looks like we came in at about an hour and 25, hour and 30 minutes. So yeah, that's it. I'll take any questions that you might have, or if that's it, feel free to log off the stream. I'll take questions for a little while before we close this down. So please type your questions. Yeah, you're welcome, Skylar, and thank you for help setting all this up. So I don't know if I mentioned this at the beginning, I can't remember, but Skylar, figured out how to do the live streaming on YouTube. This is my first time ever doing this. Skylar told me what software to download, and for about 20 minutes before we started this, I was, hurrying, trying to figure out how to run it all, and it's all thanks to Skylar that all of this came together. And thank you, Skylar, for moderating. I said admin earlier, but you're moderating. That's the term. Yeah, of course. You're welcome. I hope that this was all useful. I'm sorry to everyone for not recording this talk the first time I gave it back in November. And I'm glad that, again, special thanks to Skylar for reminding me that we need to do this. So yeah, now we have re-recorded this talk, and it is useful for anyone interested in developing Chisel. Yeah, I really hope this is auto-recording. If it didn't, I'm going to be very sad. But there was a button that they called DVR, which I'm assuming is recording, and I made sure that was checked on. So here's crossing my fingers that this actually recorded. Are there any more questions? Was there ever a push to make the builder less mutable? That is a really great question. So to give a little history, Chisel, I think, was started in 2010 with Chisel 1. I started grad school at Berkeley in 2014, fall of 2014, and by that point we were kind of late stages of Chisel 2, and they were talking about what to do for Chisel 3, which was trying to re-architect it to where you could have an IR like Fertile. I don't know about the original architecture of Chisel 3. So I don't know how close it is to the architecture of Chisel 2. I know that it's a leaner front end, so in that case it's different. But as far as the global mutable state goes, I think it's probably similar-ish. Could we make it somewhat less mutable? We definitely could do parts of it, but I don't know of any push. And so I got involved in Chisel 3 probably in 2015, early 2016, late 2015, I think. And since then, we haven't really had any push on improving that code. But there are definitely places where we could do some work to improve that. In some cases, it's not possible. It's kind of inherent in the API. In other cases, there are things that are probably globally mutable that don't have to be, and that could at least clean up parts of the implementation to make bugs less likely or make it easier to debug when they do crop up. But no push that I'm aware of. Any other questions? Yeah, of course. As Skylar mentioned, we do one thing at a time, and decoupling of Chisel to Fertile at least makes it easier to experiment with these kind of things. And and frequently we fortunately have Richard who can go in and dig into the really gnarly bugs. We have a current bug that I think Edward looked into that I believe he has a fix for, and they do crop up off and on. Okay, another question. Are you aware of efforts currently underway to bring formal verification annotations to Chisel, like front ends, the Euclid 5 backend, which is in process? Actually, yes. So let's see. So to verification annotations to Chisel. So the main work that I'm aware of, and I probably can't talk too much about it because it's currently under review, but my colleagues David Biancolin and Albert Magyar and I did some work submitting a paper integrating, that's what the Euclid 5 backend came from. That was work we started spring a year ago. And we did some work where we weren't as interested in formal annotations in Chisel as much as formally verifying fertile transforms, and so we did some work on that, and it's been submitted to ICCAD, and hope it gets in, and then can talk more about that later. But as for the front end, so there is a student at Berkeley who very recently was working on some stuff with that, where he, this is all very early, so I don't want to talk too much about it, but like he was showing that he could, at a very simple level, you could write two different forms of the same logic in your Chisel, and then it could formally show that the logic in each did the same thing. Now, it doesn't work on state. This isn't proper model checking. It was really just kind of logical equivalence checking of combinational logic. But that has useful applications in that you can, you may have some logic, and then you run through synthesis and you realize that it's not synthesizing well, so you need to rewrite it in a way that's less clear, but may use fewer gates. And so you have this nasty logic, and you don't like that nasty logic. And what you can do is you can keep the nasty logic around and keep the better logic around. And even though the nasty logic is what's actually getting synthesized, the pretty logic is what you can read, and you can formally show that they're the same thing, just inline in your Chisel. It's pretty cool stuff. I hope that he'll continue working on that, and we can talk more about it later. And yeah, other possible verification annotations. It would be really neat to have, better assertions, like currently we only have immediate assertions, but it'd be really cool if we could have like temporal assertions and then plug it into the Euclid 5 backend, as you mentioned, or even just generate system Verilog and plug it into more traditional model checking flows. Like, Yosis is a great open source one that can do some cool stuff. I really like Yosis, great work to Clifford and his team. And then of course there's the ones that you can spend a lot of money on, like Formality or Jasper Gold or whatever. So there's a lot of interest in that. I know at Sci5 we really need many of these things, and we've kind of dabbled in them off and on, but never gotten very far. There's a little bit of work that's needed on fertile annotations before it will work as well, but I think that that's all in the near-ish future. It's the type of things we need to help make Chisel more useful and more verifiable. And if anyone's interested in this kind of work, please reach out. You could call into the Chisel dev meeting, or if that's at a bad time for you, we'd be happy to set up a meeting and talk at some point. Are there any more questions? I realize that typing questions might take a while, so I don't want to, this is not like a normal talk where you ask if there are any questions and people can respond right away. People have to type some stuff. But, I guess I'll start closing. Feel free to interrupt with a question, and I'll still, of course, answer it. But, thank you all for calling in. I hope this was useful to all of you. This is obviously a bit in the weeds. But, it's important for anyone who wants to be able to develop on Chisel. Some libraries may need more knowledge of Chisel internals if you're trying to write a really cool library, or if you're trying to understand why your library doesn't quite work right. It may be related to implementation details of Chisel, and so it can help to know more about that. Or, if there's a bug that's really bothering you and we're not getting too fast enough, this is open source code, and, it's the great thing about that is anyone can read it, modify it, fix it. And it's obviously hard to dig into an open source project like Chisel when you don't understand how it works. So I hope this talk provides some amount of documentation of the implementation. I think we need more written documentation as well, and perhaps turning this talk into written documentation would be a good use of time. So I'll look into doing that and discuss that in the dev meeting tomorrow. Like I said, the dev meeting is every Friday at noon Pacific time. This is true at least as of today, April 18th, 2019. The dev meeting may move at some point. It has in the past, but at least at this point, it's on Fridays, and it has been for a while. Fridays at noon Pacific time. As Skylar linked there's some other videos that may be useful for Chisel users. And if you have any other questions, please reach out on GitHub, on the Chisel users mailing list, comment on the YouTube video, whatever. It's really, really great to see the open source community, and I thank you all for watching this video and interacting. I really do appreciate it. And to all of you who didn't have any questions or interact, I'm very happy that you were here too. It's really great to hear from you all. So thanks a lot, everyone. I guess I'm going to end the stream now and maybe chop off the very beginning when I was confused and see about getting this uploaded to the channel. Take care, everyone.